Awesome. Thank you all for joining me today for this, as Neil put it, informal talk. We'll be talking about generalization of large language models, specifically with respect to their reasoning capabilities. But I feel like phrasing it as a generalization problem makes it a bit easier to mathematically explain what is it that we want. And the moment you use the word reasoning, you will just cause a Twitter war for no reason, right? So I feel like it's much better to define when you talk about generalization. But for all intents and purposes, if you want the system that properly reasons, it's going to need to know how to generalize under certain axes anyway. And in doing so, I will try to give you a bit of a flavor of the kind of research that we do within our team, and the work that we have been doing with Neil over the past months, which I think will be public relatively soon as well, is also up that alley, although of course we've taken a more, shall we say, theoretical computer science angle to the problem rather than some... You could even say categorical, yeah. So, right. In order to kind of understand the way we are looking at language models, I think it might make sense to first spend a bit of time to talk about graph neural networks. I will just quickly ask, is anyone in the audience familiar with GNNs? Like, have you worked with them before? Okay, so I see about 50-50. I will start by giving like a very simple overview of how they work, partly to bring everyone up to speed, partly so that you will follow what notation I'm going to be using, which might be different from other papers you've read in that space. So we're going to start just briefly introducing graph neural nets, or GNNs for short. And the way they work is you have at your disposal a collection of nodes. Oh, hi Christos. Did you meet Andrew? He's in the room now. Yeah. Okay. So you have some nodes. They operate over a graph, which is, as you know, a tuple of nodes and edges. And what you do is, on every single one of the nodes, you will attach a feature vector. So node U will typically have a feature vector xu, which will be some k-dimensional real representation. And you also have some edges connecting the different nodes. And the way in which graph neural networks operate is they follow the structure of the graph in a way that's equivariant to permutations to compute higher order embeddings of each node that somehow depend on their immediate neighborhoods in the graph, right? So typically the way a graph neural network might operate is by computing a function of this form. So we go from the input space x to a latent space h in each node. And the way it works is what you first do is you compute I'm just gonna first iterate over all of the nodes inside that node's neighborhood. And for each node v, which is in U's neighborhood, you're going to compute some vector that gets sent across from U to V. So this function psi is taking two real vectors and gives you a so-called message vector, which is basically a vector that you're choosing to send from one node to the other. So nodes U and V are neighbors in the graph. And once you've computed that, this now gives you basically a mailbox full of messages, which you need to reduce into just a single vector. And this aggregation function here, O plus, is what's in charge of doing that. So typically, this takes a bag, a multi-set of these features, and gives you just one feature. This is basically any choice of a commutative monoid. So this can be sum, max, average, you know, anything which is a permutation invariant works. Once you have the aggregated message, you can then use it to update the features of the node through this second function phi, which just takes the original features, takes the aggregated message, and updates the features to some new space, right? So this is how a graph neural network operates. We call this guy here the message function, this guy here the update function, and this is the aggregation function. And these two guys, typically, the psi and the phi, have all of the learnable parameters inside a model like this, right? Everything else is fully specified by the structure of your graph. Okay, so this is roughly how GNNs operate. Do you have any questions about this, or is this clear? I will just assume this is common knowledge in what follows. Okay. Now I will briefly tell you a little bit about how do we choose this neighborhood structure here. And in doing so, we will talk a little bit about what is called graph rewiring, which is a pretty important operation. It's going to be really important when we start to talk about large language models and how they use graphs. So basically, in a lot of early applications of graph neural networks, you sort of had these graph data sets given to you, and inside them you had predefined graph structures, which sort of gave you the neighborhoods, and you sort of just assumed that this is the ground truth, and the layer never did anything to modify what these neighborhoods are. You just assumed those were the gold standard, right? And for some kinds of graphs, this might be very reasonable. For example, if you're doing drug discovery, your inputs will be molecules, and you'll have atoms connected to other atoms by chemical bonds, and there will be kind of a very nice interpretation of what these neighborhoods are. So in those kinds of inputs, you might say it's reasonable not to change anything. Okay. Now, I want to just give you a few examples on why you might want to change this graph. Okay. There's three specific things that I want to call out. So there's usually the assumption that the graph you have is perfect because this function here does not change what that graph is. You just stack more layers and you update things based on that graph. First of all, even when the graph is perfect, like perfectly explains the problem you're trying to solve, it might still be not the best graph for solving these problems. And if you want good examples of this, look no further than computer science. So one standard problem in computer science is to check for reachability. Like, is a pair of nodes connected in my graph? And I hope you can trust me when I say that I can easily be super adversarial and construct an input like this, for which if I choose to, this perfectly represents the problem I'm trying to solve, but if I try to run a graph neural network over this to check whether A and B are connected, you're going to need linearly many layers before the information from A is going to reach B, right? Specifically, if this whole node representations pipe into a global classifier, you need the path length divided by 2 layers in order for the information to mix somewhere. Yeah? However, you probably know this is a standard computer science construct. I can choose instead to represent my edges in an entirely different way, where rather than storing the original edges, I store rooted trees corresponding to each connected component in my graph. And now suddenly I can very easily check whether 2 nodes are in the same connected component, but just checking whether their roots are the same, right? And this is something you can solve with a classic union find data structure under the assumption that edges only get added and never removed. And as you probably know, while the complexity of this graph here in terms of number of steps is linear, the complexity of this graph here in an amortized sense is the inverse Ackermann function, which is less than 5 for all astronomically meaningful values of n, right? So basically, both of these graphs represent the problem you're trying to solve, and from the perspective of solving the problem, they're not dropping any information about the problem. This graph is much better than that graph for answering the questions that you're trying to answer. Okay, so that's the first example. Even when the graph is perfect, it might not be a good idea to use it. Secondly, like this is under the assumption that perfect graphs even exist. In the real world, perfect graphs are actually incredibly rare. And one of the best examples of this is, going back to the idea of molecules, is to think about something like protein folding. You've probably heard about the protein folding problem. Recently, one of the major tech outputs from Google DeepMind, the AlphaFold model, has won the Nobel Prize in chemistry, which was a model that does protein folding. And proteins are huge macromolecules with many, many atoms that fold in 3-dimensional space, and this basically determines their function. So if you try to use their raw organic molecular graph, actually a protein is a relatively simple graph from that perspective. It's like basically like a polypeptide chain, right? It's a sequence, more or less, of different components. Yeah. So if you try to run a GNN over that kind of graph to figure out how the protein will fold, you're not going to have a good time, because really very important interactions will happen to parts that end up close together in 3D space, and those might be super far away in the original graph, right? So even though chemical graphs are a really good heuristic, they're only a heuristic compared to the underlying physics, which you might, in which case all pairs of atoms will often interact, right? So that's the second thing, right? Perfect graphs don't really exist. And thirdly, and this is the part I really want to stress, some graphs are just pathologically bad. And when I say bad, I mean a model like this, which is a pretty general model and could, like, there are many papers proving that under certain constraints on like the amount of dimensionality you have here, it is Turing universal, meaning it can simulate, you can align it to like standard congestion protocols in computing theory and basically say it could be Turing complete with sufficient resources. Even though it has that capability, some graphs are just really bad, and the model is not going to be able to meaningfully learn something over those graphs. And one standard example that we often give in this space is the so-called barbell graph. Okay, like imagine I drew a clique here. I might have missed some edges. So there we go. So these two cliques here connected by a single edge. I don't know how obvious it is, but this graph is really, really bad for GNNs if you want every node from this clique to communicate meaningfully with every node from that clique. And this is a theoretically proven result, which won a spotlight paper at the iClear conference a couple of years ago, basically saying that in a graph like this with a bottleneck, you need dimensional, as the size of the cliques grow, the amount of the embedding space dimensionality you need for meaningful communication across all pairs of nodes grows exponentially with the size of the clique. So this edge here, basically, the message vector that goes through it is under a lot of pressure because it has to be the conduit of all possible communications between the pairs of nodes here, right? And as a result, you get this exponential pressure. What you get as a consequence is that on graphs like this, GNNs typically cannot even meaningfully fit the training set. We're not even talking about test generalization. Like training sets cannot be fit really well with graphs like this. Yes, Christos?
How do you quantify the amount of it? Is it an information theoretical thing? Like how do you quantify the information?
So, okay, maybe I'll write down some references if you think these results are interesting, but this original result that the bottleneck requires exponential capacity was proven by Alon and Yahav at iClear 21. And then this paper doesn't talk about measuring how much is necessary. We actually had a follow-up paper. So this is from Francesco Di Giovanni, Konstantin Rush, and others. I was also on this paper, which was published at TMLR in 2024. This paper actually shows that one very convenient way to measure how much representational power is needed is a function of the commute time between the two nodes. Now, I don't know if you're all familiar with the concept of commute times, but basically the idea is if you interpret this graph as a Markov chain with an equal probability of transitioning to any neighbor, the commute time is the expected number of steps to go from node U to node V and back. And hopefully it's clear how when you have a cliqued system with a single connector, it's highly unlikely that the Markov walker will ever jump across the bridge, right? The bigger the clique, the smaller the probability. And this is very important because, normally you would think that you need, something on the order of the shortest path length of U and V layers for the information to mix between those two. Commute time can often be way bigger than this. It can be cubic for certain graphs, right? So, and this is a very important, basically, practical impossibility result, showing that even though in theory you need this many layers for information to mix, for information to meaningfully mix, you need this much. Yeah, there's a question?
Is there any result on like what's the minimal change you can make to reduce the exponential cost? Mm-hmm. Just a minimal like add an edge or like add a couple of edges.
So from my understanding, at least in global terms, this is still unknown to mathematics. And this will be really useful to explore, like iteratively changing. The closest thing, and I will write this down as a reference, is the SDRF, the Stochastic Discrete Ricci flow paper from Jake Topping and also Francesco Di Giovanni and others. Francesco actually worked a lot on these kinds of problems, so his work is very relevant. They actually had, I think it was 2022, this was one of the best paper awards at ICLR 2022. So what they've done is they've basically related the idea of this kind of pressured bottleneck to a sort of manifold with very negative curvature, right? There is a sense in which you can generalize the idea of curvature on manifolds to curvature on edges of a graph. And basically what their algorithm does is it hunts for edges with most negative curvature and then tries to add some edges around it to loosen the load, right? But I must stress this doesn't really work in general for global structures because the way they compute the curvature is by looking at some local neighborhood around an edge. They count maybe the squares and the triangles that the edge is involved in. So if you have a more global reaching effect, it's not going to be able to model that. So I think as far as we know, like this kind of iterative adjustment of the graph to make it better, we don't really yet know how to do this in a kind of reliable way. But one thing that we did do is a more brutal approach where you don't try to iteratively modify a graph. You just sort of accept your input graph is as good as it can get. It encodes the information you have, but you intersperse it with a graph that you build specifically to be good, right? So if you combine the properties of sparsity and no bottlenecks, I call those kinds of nice properties, you basically end up with a well-known construction in mathematics. You end up with an expander graph. And we, in one of our papers with Andrea Deak and Mark Lackenby from Oxford, we have actually explored how much of an impact you can have. This was published at log 22. We have studied what happens when you just pre-compute a random expander graph and you use it as your graph at every even layer. So we took, a state-of-the-art baseline model and we replaced every second layer to not act on the original graph but to act on a pre-generated expander, and out of the box we got like 4 to 5% improvements in accuracy. So having like this division of labor where the expander takes care of global information dissemination and the original graph takes care of like the local topology seems to be a good division of labor. But yeah.
So I'm assuming it depends on the input data as well?
Yes, of course. Yes. So the great thing about the expanders is that it makes a completely uniform prior, that you're not immediately knowing which pairs of nodes should communicate at the beginning. In fact, in the work we've done with Francesco and Konstantin, the formula we get depends on the commute time as well as the expected mixing time between the two nodes, which is the Hessian of the features of those two nodes, with respect to the features of those two nodes, of the final thing you want to compute. So if you have any prior that like these two nodes need to talk to each other, these two nodes really shouldn't talk to each other, you can kind of dynamically adjust the commute times to be higher where you don't care that much and lower where you do care. The expander is kind of a globally, I care equally well about all pairs of nodes, right? But you can, of course, adjust this to fit your priors if you have priors. Yeah. Okay, so this is the general idea of the graph rewiring. And yes?
Since you're using terms like local topology, global topology,
yes.
Don't that believe that some kind of serious algebraic topology methods or something like that is going to be useful for this?
I would say so. Yeah, no, I would say so. I wouldn't say we found the right method. I think this Ricci flow is kind of the closest we've gotten, and it's captivated the attention of reviewers enough to get a best paper award, but it's not used as much. I think nowadays these like Cayley graph style approaches seem to be more favored because they're just really easy to pre-compute. This takes a long time to like compute the curvatures, to adjust the curvatures, and even then kind of it's only locally fixing the problem. So yeah, I do believe that we can find a solution by understanding better algebraic topology methods, but I don't think we have a solution quite yet. Yeah. Okay, so If currently it isn't clear to you why is all of this relevant for large language models, don't worry, it will become pretty apparent when we move into how they operate, which is basically going to be now. Okay, so I am going to erase this. Oh, good point. Good point. Okay. And now we're going to talk about LLMs. Or specifically, we're going to talk about how the modern transformer stack operates. Okay. So I trust many of you, or even all of you, are already familiar roughly with how a large language model operates. I'm just going to distill it back to some of the key elements so that we have a kind of clear reference point and to align the notation from what we were talking about before. So let's imagine I have some text, like a house of, and I want to complete this to be like a house of cards. The way this model will typically process this bit of text is it's going to cut it up into pieces, which we call tokens. And actually, in this case, as far as I'm aware, the Gemini tokenizer will exactly treat each word as a token. In reality, it might be parts of words, it could be multiple words, depending on the frequency of usage in a text corpora. And what you'll then do is for each one of these form part of your vocabulary, you are going to compute a embedding vector, which is differentiably learnable. Like you basically learn a lookup table for every single token. And then you interleave two different types of layers. One type of layer is a feed-forward network. So this is just your usual kind of stack of linear transformations with nonlinear activations applied in a shared manner to every single token separately. All right. So this guy here, you might imagine it as something like you apply a learnable affine transformation with a learnable weight matrix and learnable bias vector. You apply some activation function to this, and if you want to, you can stack more layers. So you can add a second transformation to the outside of it. Right, so this is your typical two-layer, multi-layer perceptron, nothing too complicated here. The parametric parts are the W's and the B's. Okay, so once you have these guys, this is one type of layer. The second type of layer that you will encounter in a system like this is the so-called attention layer. And inside this layer, I'm just gonna wipe this so I have a bit more space. What's going to happen is you're going to get some kind of aggregated embeddings of each token, and it's going to work in a way where a token will send its information to all of the future tokens. So the way it works is if you want to compute, say, Z of off in this case, this is going to be computed as a sum over all of the other words, which are a house of. And you will be computing some kind of coefficient telling you how much is that word relevant for off, multiplied by a value vector, sorry, there's an H here, H of the word. Okay, and the way in which the alpha coefficient is computed is by computing a dot product between the corresponding query vector, and the query is attached to the receiving item. So there is a query vector multiplied with the vector for the receiving item. And then that is, you take a dot product of that with the key corresponding to the item that you're attending over. And then the resulting items are normalized using a softmax function. and that's multiplied with this guy over here. Okay, so I hope this function or some version of this function should already be familiar to you. And once you have these updated embeddings, you kind of repeat these two types of layers for sufficiently many steps, and at the end, you use each embedding to predict the next token. So in this case, you have ZA to predict house, Z house to predict off, and Z off to predict cards, for example. So the reason why I started this talk talking to you about graph neural networks is if you look closely enough, there is a graph here. And even though many people think about transformers as sequence models, they're actually secretly graph models under the hood. And thinking about them as graph models can actually make it way more obvious why they fail in certain ways than if you think about them as sequence models. And I'll show you this. Like some of these simple ideas we talked about with graph rewiring and why certain graphs are bad, we will very quickly understand how this graph is actually a really bad choice. Okay? But, first things first. We'll get to that. I just want to check that this diagram is okay with everyone, that you understand why this graph here only has edges pointing forwards, because you don't want to cheat by giving the information for the next token into the thing that's supposed to predict it. And also that you understand why there exists basically a graph here, because a word is basically talking to other words when it's computing its own representation. Yeah, so is that all clear? Are there any questions? Okay, so I'm going to leave this here, and I'm going to get rid of the graph rewiring material for now. And now we're going to start with our first I will explain to you what is the flavor of generalization problems that we care about in our team, and then we're immediately going to start to unpack one of such problems that transformers have, partly because of this particular choice of structure that they use. So, the key problem that we care about is out-of-distribution generalization. But because out-of-distribution generalization is something, and this is like the essence of reasoning, right? Like if you want to have a system that truly understands a certain kind of computation, it should be able to run that computation at least with some predictable error as you change the inputs across all legal inputs, right? So even as you drift away from the inputs you use to train the system, it should still, at least, even if it fails, it should fail in a predictable manner rather than completely collapse on itself, right? That's generally what we mean by out-of-distribution generalization. But because this is relatively tricky to define what a distribution shift is, what we practically focus on is actually length generalization. So what this means is, if I've trained my system to predict the next token, to answer questions with inputs of up to n tokens, how will it behave when I give it 2 times n tokens, or n plus 3 tokens, or something like that? Like sizes it has never seen at training time. This is a really good problem to study for 2 reasons. The first reason why it's a good problem to study is because it's a really well-defined problem. Like you know how many tokens you have, you can then study what happens when you go away from the training set. What's really cool about it is you can often prove best case results, right? Like when it comes to these kind of size shifts, usually when you write the paper and you say transformers cannot do X, someone just will counter you by saying you can just change the data set and improve it that way. When you talk about size generalization, you're starting from the assumption that you've trained up to this many items, and you check what happens when you go away. Any particular training set must be fixed. So at some point, you're making a conscious decision not to go beyond this size, and you're then interested in what happens beyond that. So this is the kind of result that cannot be countered by smarter data, smarter algorithms, or smarter something. It's really a fundamental property of the architecture if I prove that it cannot generalize. That's the first thing. The second thing is that it's a super practical problem. I don't know how obvious this is, but nowadays we are being flooded with large language model-based systems that can reason over really long horizons and solve many problems within the same context. Language models like Gemini, which we offer at Google DeepMind, have context windows of up to 2 million tokens. I don't know how obvious this is, but these systems are typically not trained over 2 million token context windows, okay? They are trained over smaller context windows, and then you try to train them in a way that you can get good length generalization, because it's really hard to train on big context windows for a long time, right? So it's a really practical problem. If you make meaningful inroads on solving this, you can very meaningfully influence the direction in which AI systems will continue to develop, especially as they get more agentic, right? So it's both an important problem and a well-defined problem, which is something that we like, because it will help us prove things, and it won't be just, a potentially, useless proof. It will be actually a proof that might translate into meaningful modifications we can make to the system. Okay, so without further ado, let's study a particular length generalization problem, copying. And I'm not even going to ask you the hardest possible version of copying. I am going to ask you to copy one element. You would hope transformers can at least do that. No, they can't. But anyway, so I'm going to show you two different prompts. The first one is find the first digit of 0, 1, 1, 1, ... 1. And the second one is find the last digit of 1, 1, 1, ... 1, 0. Right. The answer to both of these should be 0. As you might expect, as we increase the number of ones, all frontier AI systems will collapse, and they will start to output 1 when they should output 0. But there is another interesting aspect of it, and I'm actually going to start by asking you to give me a show of hands, like from your prior assumptions and your understanding of how these systems work. Do you think this query is harder? Like, do you think it's harder to tell what the first digit is? Raise your hand if you think this one is harder. Okay. Raise your hand if you think the last digit is harder. Okay, so more of you said that the first digit should be harder than the last digit. Neil, I think you might have read this paper, so I'm not sure if you count. Yes, spoiler alert, this one is the harder one, which to us humans sounds really preposterous, right? Because people sometimes try to anthropomorphize these models too much. They don't think like humans. Yes, of course, for us it's much easier to say the thing that's the last thing we heard. But for these systems, actually, predicting the first digit is way harder in the sense that they will collapse way sooner compared to these, they will collapse way sooner for these inputs compared to these inputs. Now, let's try to understand, first of all, why exactly does this collapse happen? And that will then hopefully also explain to us why is this so much easier than this, even though we're not expecting that. So, basically, first, let's think a little bit about the way the data flows inside this system, right? So you have your, say, 5 tokens, all ones, followed by a 0, and then they will update to create some high-dimensional embeddings. And remember, our choice of graph structure dictates that information can only flow forwards. Sorry. Yeah. And then you can do this again, like you stack more layers. And every step of the way, you have a connectivity pattern like this. And what happens is the way the next token prediction works is, right, who is responsible for predicting the answer? Only this guy over here, right? So this here is what predicts the output for this particular sequence, right? So first of all, because I have this bottleneck over here, remember we talked about bottlenecks earlier, what's going to happen is, and this is a theorem that we have been able to prove, is that as I increase the size of the problem, no matter how well I train the system up to a certain point, as I increase, for any epsilon I want, I can bring two successive sequences. So a sequence like this and a sequence like this with an extra one. I can bring the embeddings of these two zeros below any epsilon I want. And this is in the infinity norm, to be precise, right? So what this means is I can just set this epsilon to be my machine epsilon, right? And I can increase n as much as I need for that to happen. And at that point, these two sequences that are different are going to have up to machine epsilon same embedding in the last token. And at that point, the model has no way of probabilistically answering those two sequences differently, because it's going to get exactly the same, indistinguishable to a computer embeddings. And one thing I must stress, if your knowledge of machine epsilon comes from, computer science undergraduate level numerical maths courses, and you might think this is a relatively small quantity, modern AI systems are not like that. Modern AI systems are trained at most with bfloat 16s, which are 16-bit floating point representations. But nowadays, you have a lot of mixed precision training with 8 bits, and you even have, when the models are served, you have even quantization, which further caps the amount of values that this floating point type can represent. In reality, all of these things push machine epsilon up to crazy amounts, and as a result, the models crack well before our theory says they're going to crack. Okay? So this is the reason why the collapse happens, like why the models are not able to generalize on these two types of queries. And now, so when you see the graph structure laid out like this, now hopefully it should be a bit more obvious why this one was the easier one, right? Because if I start from an earlier position, how many different paths do I have? I have this many paths, right? And if I start with a token, it's towards the end, how many paths I have? Only one. And this is only with 2 layers. Modern transformers will have dozens of layers or even more than that, right? The amount of paths allocated to earlier tokens grows exponentially compared to the number of paths allocated to late tokens. And we can even prove, this is another proof we have in our paper, that as the number of layers goes to infinity, as you might expect, only the first token ends up mattering. All the other tokens get wiped out from the bottleneck, right? And this is what we mean. The model is topologically predisposed to favoring things that are early. And this is a kind of baked-in consequence of the fact we chose to train them in this way. And that is the reason why things that are towards the end are discouraged. Now, of course, you will very rightfully say that in the English language, to predict the next token, usually you only need to look at the past few tokens. So the model tries its hardest to protect this information, right? It learns a recency bias. It has position embedding, so it will try to really focus its attention on the last things. But only up to the sizes it's been trained on, right? You go on bigger sizes, numerically things start to fall apart, and you start to see numbers of items you're normalizing over that you haven't seen at training time. And it starts to give way, and it starts to collapse. And these tokens tend to survive a lot longer compared to these ones over here. So this is the first paper that we have done in this space. If you want a reference, it has a really fun name. Transformers Need Glasses, from Federico Barbero and others. It was just recently presented at last year's NeurIPS. Okay, so this is one piece of work that studies linked generalization and kind of figures out that because of the shape of this graph, you're not going to have a good time. Okay, are there any questions on this before I move on to the next one? Yes, Christos?
I have a comment.
Okay.
It's actually worse than what you described, because different hardware and different network topologies, depending on how good your network is, have different different tolerance. We test the kernels with different tolerance. So even if your machine, like the matrix multiplication and all those kernels are not bitwise the same.
Yeah.
We have a huge tolerance that might be even like 0.1 or something.
Yeah.
So it's way worse than.
That is completely correct. Christos here is a compiler engineer in the Gemini team, so he will know a lot more than me about the specifics of how bad it is. But yes, it is worse than what our abstractions say that they are. Yeah.
So it just becomes like a graph rewiring problem?
Yes, I mean, we will talk about, I hope I'll have enough time to talk about graph rewiring towards the end. But yes, this is one strategy you can do to fix the thing. Yeah. Okay, there are two different things you might say in response to something like this. The first thing you might say is, hang on, we're talking here about these paths as if they're all completely used, but there is actually an attention mechanism here which could attenuate some of these edges and make things a bit easier. And that's to some extent what the attention mechanism tries to do. For example, it will really try to keep these links alive as much as possible, right? At the expense of some of the earlier ones. So in theory, if the things that come into this softmax function are spread in the right way, you might save yourself from the problem of this graph being bad by just rewiring yourself automatically. And I would argue, if you've read some mechanistic interpretability papers, especially, they discover these interesting induction heads inside the attention, which are really sharp operations that kind of learn to kind of, very closely, sharply attend over things like successors. So there's a head specialized to do +1, but a generalized +1. So like if there's a 1, it will attend to a 2. If it's a Monday, it will attend to a Tuesday. If it's a January, it will attend to February. So like there's a head specialized to do generalized +1. And it learns these kinds of mechanisms, right? So there are many hard pieces of evidence that the model learns this kind of circuitry to kind of use the attention to only direct the graph to parts that are relevant. Well, we have some sad news, which is that these circuits are definitely not circuits in the computer science meaning of the word, and they will also collapse when you do size generalization. So all of the mechanistic interpretability papers take place on in-distribution inputs, on inputs of the same shape as the ones the model was trained on. What happens when you go beyond? We have a follow-up paper called Softmax is Not Enough. And this is a paper, I rarely get the chance to write first author papers these days, but this is a thing I was quite passionate about, and I really tried to make the point of leading the theory and the implementation for this one. We released it last year. And in this paper, we basically show that as the size generalization grows, softmax cannot stay sharp, right? And this is where, like I told you at the beginning, this choice of tokenization is going to become important. Now you're going to see why it's important. I'm going to explain to you a very simple proof that we can make for this fact. So what we can show here is that even if you have a really sharp attention, so let's say you need to predict a maximum in a sequence of tokens. So you have 0, 1, 0. And your model learns really nicely to attend over that 1 in the first instance. What I can prove to you is you can add a bunch of zeros or a bunch of garbage, doesn't even have to be numbers. And provably, no matter what are the tokens that you add, no matter how well you've trained your model, past a certain n, I can bring down this coefficient on the 1 below any epsilon you want. And once again, when that epsilon is less than machine epsilon, you're pretty much screwed. Now, why does this work? I will very quickly enumerate to you the mathematics behind how we prove this. Because you have a fixed tokenization with a fixed vocabulary, after you've trained your model, there is a fixed set of embedding vectors that you can have as your starting point, which means your space of possible representations is just spanned by these initial embedding vectors. Now, every layer you do is either a continuous function, like this feed-forward network or this matrix multiply over here, or it's a convex combination of the things that you already have, which means you're basically always moving from either the set of points or the convex hull of those points, or going from one convex hull to another convex hull. This is a statement known at least to Weierstrass, that like a continuous function takes you from a compact space to another compact space. And this means that the thing which governs your coefficients, which is, well, the actual unnormalized version of it is the exponential of this. This thing will also be in a compact space, so a compact subset of R. Yeah? And we have a separate lemma showing that if you have a constant bound on how big your unnormalized logits can get, as n grows, your coefficients will go down as big theta of 1 over n. And that's it. Like, doesn't matter. Like, the model basically tries inside its training data to learn how to make really big logits for the 1 and really small logits for the 0. But there is always going to be a constant bound on what it can do to spread them apart. And as you increase the items, the constancy of the bound means you can abstract it away and you're just left with 1 over n decay rate. So the culprit is the tokenization. The fact that you have a fixed set of tokens and you cannot move beyond the fixed set of tokens kind of condemns you to behavior like this when you generalize in size. Well, that and the fact you're using continuous functions, but that's something we can get rid of a bit less easily. Okay. So, of course, another assumption which relates to the question you've asked is also that you have a head which globally attends, right? The thing which makes this go as 1 over n is the fact that as n grows, the last token will attend over ever increasing number of things. So, one other thing we can try to do is graph rewiring to hopefully reduce what n is and that way escape the confines of the theorem. And this leads us to the final paper I'm going to discuss today, which is what makes a good feed-forward computation graph. And this is work from Alex Witwicki and others, which we released last month. So, first of all, why do we need, for better or worse, we need the graphs to be of this shape for the time being, because this allows you to train at much larger scales than if you didn't have this. Strictly speaking, you could use a fully connected graph here, and that's totally legal at inference time, but then at training time, you cannot do this, where you kind of have a sentence and then train on different parts of that sentence at the same time, because illegal information is going to flow into the other nodes, right? So for better or worse, to allow us to train on, trillion scale data sets, we need this graph to only ever go forwards. And that's what we mean by the feed forward part. But as we've just discussed, as mentioned in the Transformers in Glasses paper, this feed forward graph here is actually quite bad. So maybe there are better ones. And who knows, maybe there's something like the expander graph was for undirected graphs that we can use to improve things here. Well, we worked on this with Mark Lackenby as well, who worked with us originally on expander graph propagation. He's a mathematician at Oxford who has expander graphs as one of his specialties, and he scoured the literature, and unfortunately there wasn't really that much literature in pure math on what is a good graph that only is allowed to go forward. There's not actually that much literature on this. So we ended up realizing we have to basically invent new math in order to be able to talk about this. And the first thing that was a quite sad result for us is that there's probably no such thing as directed expanders, in the sense that you can take an expander graph and orient it. It's actually going to be quite bad, especially if it's a sparse expander. The probability you're going to create sinks in this graph is really big, and that means information cannot flow into the final node. This is not good, right? So you want there to be no sinks. That's one thing that will be quite useful. And then, assuming you have that covered, we found two other properties that are sort of, aspirationally related to properties that expander graphs satisfy in the undirected case. The first one is mixing time. So specifically, low mixing time would be a good property. Now, of course, it's not the same kind of mixing time as in a irreducible Markov chain. Here, the information can only flow forwards, and eventually it lands in the final token. So here, it's really the amount of time it takes to mix into the final token, right? So you're sort of measuring, if you define your kind of walk matrix from U to V as you kind of start from a particular position and then you kind of follow the out degree of each token to gauge the probability of where you end up. So it's like 1 divided by the out degree of node V. This is how I'm going to denote the out degree, in case that V to U is inside the set of edges, otherwise 0. I can check, like I raise this matrix to a power, this simulates a random walk. And I start with some initial probability distribution. I can check how many T's do I need, how many steps do I need before it becomes reasonably close to a unit distribution, the final token. And I think usually you'll take a cutoff like a quarter or something like that. So, but this is an arbitrary choice. So this is one measure you can try to satisfy, having as low mixing time, which is this T here. Like, the smaller the mixing time, the quicker the information travels from all parts of this graph into the end of the graph. This is a good property to have because it means you won't need a super deep network to propagate information. Yes?
So your unit transition probabilities are uniform?
Yes,
Why
yes.
did you change that?
So, that's a very good question. We haven't really gotten there yet. This is very recent work. But the reason why we're going to assume everything is uniform is because we're measuring kind of the inherent usefulness of this graph without taking into account what attention mechanisms can do, right? Because that's sort of like, how good is your template topologically speaking, right? If you take into account attention mechanisms and learnability, I'm sure you can find lots of other useful results, but this one is a nice result because it really kind of abstracts away anything about what is being learned on the system and just talks about how easy it is, I guess. But mixing time is only one axis. You also want that information to reach the final node integrally, right? You don't want this node to be overwhelmed by this node, as we discussed before. So we found a complementary measure of fidelity, which we want to be as high as possible. And this is like a converse process. So here we talk about how information moves into the tokens from its senders rather than the other way around. So in the case of fidelity, now it's 1 divided by the in degree of U for every V to U and 0 otherwise. Note that this doesn't give probability distributions anymore. This assumes you're kind of diffusing the information completely at every single step. And it tracks like what's the coefficient of a particular item as it travels in the space. So you take the delta, you raise it to a power of t, and that tells you in its final row, it will give you, so in the n minus first row, this will give you what's the coefficient of each item in the sync node after t steps of diffusion. Yeah. Now, of course, you don't want to let t grow as much as you want because, as you know, the first node, if there's no sinks, the first node is going to overwhelm as t goes to infinity. So actually, what we are hunting for is the most favorable, t, the most favorable number of layers for a particular node, minimized over all of the nodes, right? This is what we call minimax fidelity. And the idea is you're searching for the worst case node, the node which has the smallest chances of making it into the sink, and you're tracking when's the most that node has made it into the sink. And this is, if you assume good residual connections, this is the most worst case information you can retain in your graph. Okay? And I just want to stress that simultaneously optimizing this down and optimizing this up is extremely hard. So a fully connected graph, a fully connected causal graph, like the one we have here, its mixing time is actually pretty good, is log n. So I like that. But its fidelity is, as you might expect, only 1 over n, which is not that good. Like it can only ever take an average and that's it. Yes?
Do I think that the fidelity matrix is talking about the mixing matrix?
Yes, I think that's a good way of thinking about it, but we haven't really been able to kind of relate the two very easily because because this matrix, is only unidirectional, you can't think of like nice spectral properties and things like that you can relate between them. But yes, you could think about it as a potentially as a timer. But this is not a probability distribution. This is also an important point. And then you have like line graphs, which are kind of the opposite approach, where you only allow neighboring nodes to talk to each other. This is how recurrent neural networks work. They have a really good fidelity. We can prove using Stirling's approximation that the fidelity is root n over n for those kinds of graphs. And this is obviously much better than 1 over n. And the mixing time, unfortunately, is linear, as you might expect. So we struggled to find something that optimizes both of those. So we asked AI and combinatorial optimization to help us find something. And the last thing I'm going to present to you is what AI told us we should be looking at. So this here, I'll express it as its adjacency matrix. So the way it works is you have this like strip over here, which is connected. So neighboring nodes are connected. And then you have these squares here. Okay? So these here, what this approach is doing is it's basically chopping the graph, chopping the tokens into blocks, and then doing bipartite graphs from one block to the next. Right? We then use some knowledge about bipartite expanders to sparsify these squares significantly and also sparsify this local strip significantly. It turns out that with a graph like this, you can prove under certain assumptions that the mixing time is polylog, which is good. The idea is to represent this as a sort of Markov chain, where you have some probability of jumping into the next square and some probability of staying in the current square. And you can show that it's a polylog if you have the right ratio of the sizes of the items. The fidelity we still don't know, but we found that the coefficient of the 1 over n is highly controllable by how much sparsity you put in each one of these bipartite graphs. So while we don't have a proof for the fidelity, we know that it's some kind of OK over n where the k is quite controllable. And when we train on a structure like this to predict things like the maximum, second maximum, or parity, which are typically hard problems for transformers, we cut out a lot of the edges out of the original fully connected graph and still retain a really good predictive power. Okay, so this is only the first step of like trying to find what is a good graph that only goes forwards. We believe there's a lot of math to be done here, which still hasn't been done. And we believe it's a problem worth studying because for better or worse, in the coming years at least, maybe even decades, we're going to be stuck with graphs like this. So we're going to have to try to make the best of them. All right. Thank you very much for listening.
Any questions, Ryan? I'll ask a question. So I read your GNN paper, and I kept seeing cardinal algebra maps, you know. Is there any potential utility in phrasing some of these discussions in those terms?
I would say there definitely is. I don't know how obvious it is, but we are still very much in the early days. A lot of these papers have only been presented in the last 4 or 5 months, and we're only just now starting to think about all of these computations in terms of graphs. Or well, we've been thinking about it in these terms for a while, but we only just now started to dish out papers which like explicitly prove that there are some things these models cannot do as the size increases. I definitely think more constructs from computer science cannot harm and should be introduced. And that's part of the reason why we're collaborating, among other things. So yes, I do believe that.
I mean,
Yes.
it strikes me that rewiring sounds like naturality, potentially.
Potentially, yes.
Yeah,
Okay.
he gets to talk to him every day.
Sound like bipartite graphs, so I'm thinking like simplicial complexes as well. So you're kind of encoding like three-way interactions, maybe multi-interactions. So maybe that could be somewhere you can look at. Probably think that.
For sure. I mean, you have to deal with a sort of trade-off here in that, like, there's well-known results in GNN theory that as you increase the cardinality of how many nodes can interact at the same time, you provably increase expressive power. You can align it with various versions of the Weisfeiler-Lehmann algorithm if you want to kind of see proofs of how that's done. But you also have to deal with just the storage and time complexity of what you're doing here. So we have really good efficient operations to compute all pairs interactions and to compute one scalar per item. This is basically a huge outer product, right? And we have, Christos can tell you more about that. We have really efficient ways to do that. And then anything that kind of goes beyond that and has to store more items, it's going to be more of a pushback to use it meaningfully in a really large scale system of today. Maybe, a decade from now, this will be easier because we'll have better hardware for dealing with simplicial stuff. But in the realm of very fast matrix products and very easy to store quadratic but not higher than quadratic things, that's where I think we hit a bit of a roadblock. But I fully agree with you. We should be thinking about higher order interactions. Maybe one trick about this is, and we've explored this in a related paper some months ago, is you could imagine you have a small cache of reasoning tokens, and those are much smaller than your original sequence, and you kind of do higher order computation on those and kind of allow this quadratic part to talk to them periodically. But obviously, how do you connect those? It introduces a whole new space of design decisions that you need to make. So it's a bit tricky to figure out. Yeah.
I want to throw out this provocative question. Why are we bothering with all of this when we could have the LLM? Why do we care about copying the last element when we could have the LLM write a program that does it? Or why teach the LLM to sort when we could get it to write some code to sort and then execute it? Why are we in this business? Okay,
Christos is basically reminding me of something I forgot to say. Basically, yes. So the reason why is because we want to build agents. That seems to be currently the hip word of the day. And the point of the agent is that it should be capable of taking a complex task, breaking it into pieces, and then using solutions from one part to autonomously answer the next. And what I'm seeing time and time again with the current top class of models is you'll give them a hard problem. They will even potentially write perfect code to solve it. They'll get the right output. They will fail to copy the output into the final answer that they give. And basically you need, in the current state of these systems, you need humans to supervise them and to be very careful and launch the code themselves to kind of double check that everything is as is expected. And I think that, the longer horizon the tasks that you give to the system, the more you're going to hit these exact roadblocks that we find in our theorems. And basically, I don't think there's a way to walk around it in the general case. You're going to have to do some things to deal with this. Maybe it's one of the things that our theory proposes. Maybe there is something else. But I think we have to collectively think about this because it's not enough to just say, if there is you as a human supervising the system and using the code yourself, sure, that's fine even today. But if you want to have a multi-step chain of thought with code execution in the middle, you're going to need to think about some of these things, I think.
Okay.
What about, I'm sorry.
Go.
Yeah, so you were talking about length generalization. What about other kinds of masking of the input? I'm assuming user inputs is full of type notes.
Of course, no, we have discovered all sorts of wacky behaviors. For example, another thing about this is that generally vocabularies in modern language models are huge. They contain lots of different combinations of words, and sometimes entire snippets of boilerplate C# functions ended up as single tokens. And it turns out if you ask a model to do something with that token, you can send it in an infinite loop and jailbreak it, basically. So, there's lots of very interesting vulnerabilities that happen when you ask a model, maybe not something it hasn't seen, but something it's seen very rarely in a text corpus. So, yeah, they're all super interesting to us. Size is just maybe one that's easiest to attack and kind of theoretically reason about. But yes, absolutely, all kinds of distribution shifts are fair game. It's just that because everything is tokenized, you don't really get the kind of value generalization you would get with arbitrary real numbers. So there, you don't have to worry about that one as much. And size is just kind of the easiest one. Also has a lot of previous research that's been done to kind of analyze the problem. But yeah, you can totally do other things as well.